Okay, so today we're going to talk about induction. Induction is one of the mathematical ways that we can use to prove something, especially with integers, with natural numbers. These things have just a very suitable value for induction because that's sort of where it got started and where it's used the most. So, a brief history of induction proof. Uh, a lot of mathematicians actually used induction in their work. It was not formalized in 19th century, but before it was kind of widely used. Not really recognized as one of the valid proofs, but starting from Plato, basically, in the Greek mathematic era, 370 BC, he basically used the induction to prove some theorems about natural numbers. Also, Euclid, he used induction to prove that prime numbers are infinite. This is also what we're going to be looking into when we learn the induction concept. And then later it was the Persian mathematician Al-Fakri, if I'm not pronouncing the name wrong. He used that to prove the binomial theorem, which has a relation to some of the later work, which was finalized by Pascal. Yes, it's actually connected. His triangle is basically just something that documents the coefficient of the binomial theorem stuff. Pretty cool. They all used induction in their work, as well as Fermat. At the time, he called it an indirect proof by infinite descent. Basically, I can explain to you what it means in a bit, so you'll understand why he called that. So by infinite descent, that's sort of the key word of it. And this is like in the 17th century. So basically that was almost closer to the modern era of math. Not quite. And then it was Bernoulli who had his famous inequality, which could be now very easily proved by induction. And now the concept of induction is finally modernized and popularized by these three, and actually there's more mathematicians, but these three are sort of like the famous ones. The George Boole, the one famous achievement, maybe Boolean algebra values in computer science. Augustus De Morgan, he had the infamous De Morgan's law, and Giuseppe Peano, which I think had the most contribution because he had the axioms, which are sort of like fundamental beliefs, and he also was one of the inventors of the theory of sets, which a lot of these are interconnected. So what does induction mean? So let's read through the principle of mathematical induction. It states that a statement, I'm just going to switch to black, a statement about integers, so we're starting with integers because, well, induction could be used for a lot of other things, but we're starting with integers. Statement about integers is true for all integers greater than or equal to 1 if these are the conditions that would stand true to allow the truth for this statement. So the first one is that it is true for the integer 1. And the second one is whenever it is true for all the integers 1, 2, and k, then it is true for the integer k plus 1. So what does this actually mean? Let's say that we have a set of integers from 1, 2, 3, 4, 5, 6, 7, and 8. We want to prove that fx for x is within the set of, we'll call it s, x is within this set of integers, that fx is true. So how do we prove that? Okay, just to clarify, by it's true, it can be anything. It could be fx equals another function, or fx equals a certain value, or fx doesn't equal something, or just something that describes fx that stands. So how do we prove that all of the integers in this set is true for fx? One, you could prove it by testing all of the integers. So f1, is it true? Yes. f2, is it true? Yes. That would be too much work, especially when you're dealing with a whole like 3,000 set of integers, or sorry, 3,000 elements in a whole set, or you're dealing with all of the integers. So what do you do here? Basically, what this kind of principle is telling us is that we have one which is applicable. We just try only one of them. So f1, we see, oh, it's true. Then what we prove is that we prove wherever this number is, we'll call it k plus 1 must also be true. This is powerful because it can sort of just loop on forever, because you see this is k plus 1 is true. So if 1 is true, then 2 is true. And then we all know that 2 is also true. So if 2 is true, right, 2, now we set that as k plus 1, 3 is also true. And then we can keep going. We can say 3 is k, so k plus 1, 4 is also true. So all the ones that I circled are true. Right now we can just go on forever. 5 is true, 6 is true, 7 is true, 8 is true. Essentially, you can interpret this whole thing as you have a starting point, which is 1. You prove that f1 is true. And then you say, oh, if 1 is true, then 2 is true. And if 2 is true, then 3 is true. If 3 is true, then 4 is true. Essentially, you prove that by having, if fk is true, then fk plus 1 is also true. How about let's look at some examples so that you can better understand the concept. Let's look at an example where inequality appears. So 2x bigger than or equal to x plus 1. This is our equation. We want to prove that it stands for all the values of x within the positive set of integers. So this symbol denotes the positive set of integers, 1, 2, 3, 4, all the way to wherever you can go. 2x is bigger than x plus 1, or bigger than or equal to. So remember, firstly, we prove a starting point, x equals 1. And then secondly, we prove that for all integer, we'll say x here because x and k are just variables. For all integer x here, if x is true, means that, x plus 1 is true. Remember, so for x right here is true, then x plus 1 is true, and then this could be the new x, and then x plus 1. In this case, x plus 2 is true, and then x plus 3 is true. We could prove basically all the way that all of these numbers are true. So let's get started with the first one. X equals 1, pretty straightforward. On the left-hand side is 2 times 1 equals 2, bigger than or equal to. X plus 1 equals 1 plus 1 equals 2. 2 is bigger than or equal to 2, obviously, because 2 equals 2, and this is proved. The second one, I want to prove this. So if we look at it on a number, actually only this. If we look at it on a line of numbers, we already proved that 1 stands, right? 1 is true, and then we want to prove that all of these, so for any x, right, x plus 1 is also true if x is true. So now we assume that x is true, so 2x is bigger than or equal to x plus 1. Now we just want to find out how we can prove when x is x plus 1. So now we substitute x in for x plus 1. So 2x plus 1 is bigger than or equal to x plus 1 plus 1. So now we want to prove the existence of this if this is true. So now we get 2x plus 2 bigger than or equal to x plus 2. Take the bracket out. So also minus 2 on each side, 2x bigger than or equal to x, which is always true when you have positive integers, of course. So we proved the second one as well. Essentially, using these two, we can prove that this inequality exists for all x within the positive set of integers. Let's look at it from more of a visual perspective. I'll draw y and x. So let's say that 2x is this line. X plus 1 is just 45 degrees, but you move it up a bit. So 1a, 2a, or just you know that the ratio of y and x is always y is 2 times of x. And then the second line right here is x plus 1. So this would be 1. What is this? This is when 2x equals x plus 1, which x equals 1 because 2 times 1 and 1 plus 1, they are the same thing. So x equals 1 here. X equals 1, that pretty much means that all of the positive integers, including 1, satisfies this condition because this line after this is always bigger than this line. It's growing much, much faster. And it started with equal to the other line, but it's growing much faster. So this is how you look at it from a linear perspective and then prove it. But using induction, let's review the logic. Using induction basically means that you have x equals 1 is true, and then for all of x plus 1, x plus 2, x plus 3, you can basically prove that it's true because through this step, right, through the step of proving that if x stands, then x plus 1 stands. If you prove this, then you can basically go on forever and ever and ever and ever because this is kind of like the method that allows you to keep adding 1 and adding 1 and adding 1 and prove all of these are true. And let's look at something a little bit more difficult. Let's look at the sum of integers. So sum of let's say 1, 2, 3, 4, 5, 6, 7, all the way to n. So if you remember from certain formulas or you have derived it yourself or anything, n times n plus 1 divided by 2, that equals 1 plus 2 plus 3 plus 4 plus plus n. There are a couple ways you can prove it. One is just very intuitively you line all of them up. And then you have this number and this number together, which is m plus 1. This number and this number together, which is also an m plus 1. And then how many are there? There are n divided by 2 in total. So n divided by 2 times n plus 1, eventually you'll arrive at this formula. I didn't provide you with a very good proof here because this is not the point. Literally, you can prove it yourself. But the point I want to address is induction. So in here, you don't even have to think about lining them up together, pairing it, all of that. You can basically think of it as, firstly, you prove that for n equals 1, it is true. So for 1 plus, there's nothing else because 1 is just 1. So 1 equals 1 times 1 plus 1 divided by 2 equals 1. So we already know that this equality is true for 1. Check. So let's prove it for n plus 1. So again, if n is true, then n plus 1 is true. That's what we're trying to prove here. So let's assume that n plus 1 divided by 2 equals 1 plus 2 plus 3 plus plus n. So now we use now we use n plus 1 in the position of n. So n becomes n plus 1, and then this n as well, it becomes n plus 1, and then plus 1, as the bracket says, divided by 2 equals 1 plus 2 plus 3 plus all the way to n. And then plus n plus 1, because right now n plus 1 is in the position of n. So how about we take it apart right now? So n plus 1, that's just n plus 2, isn't it? So n plus 1, n plus 2 divided by 2 equals 1, n plus 1. Now we take the 2 apart, so n plus 1, n plus 2, n plus 1 divided by 2 equals 1 plus n plus 1. So now we have these two and then these two. So 2 n plus 1 this is the first one, and the second one is plus 2, and then it's 2n plus 1 equals 1 plus 2 plus 3 plus 4 plus n plus 1. This is the new n. This is the new n. This is new n. But right now we have the old n here represented by this. And this equals to this, right? So this is assuming that the condition is true. So right now we're just proving that this whole thing is true, assuming that this equals this. So essentially, on the both sides of the equation, we can just delete this. So with this gone, with this whole thing gone, 2 over 2 n plus 1 equals n plus 1. And then 2 n plus 1 equals n plus 1. This, of course, is true. So that now we proved, firstly, that for n plus 1, this whole thing is true. Now for any n is true, then n plus 1 must be true. We prove that if this condition stands, then at the end, the whole thing with n plus 1 is also true. To repeat it, if this condition stands, if the condition with n stands, then the condition with n plus 1 must be true. It stands because we just sort of juggled around the equation and then figured out at the end it's all the same thing. So this equals this, based on these two observations. If you think about it, it's really just n equals 1. That is true, right? And then we're saying that if n equals any for any n, then n plus 1 is also true. Then that's 2, right? Now we have 2 as n, then n plus 1, which is 3, is also true, right? Now we have this as n plus 1, 4 is also true. So 1, 2, 3, 4, all the way you can go to infinity. All of these can be proven by induction, and it saves a lot of time. It saves a lot of energy for those who want to think about the whole thing and then figure out, oh, this is actually the way to solve it. This is actually equals to this. You can use induction to prove a lot of things. Let's look at a slightly more difficult induction proof. So for those of you who have learned the geometric series, essentially the series, so a plus ac plus ac squared plus ac third plus ac fourth plus ac fifth, This is a geometric series. You can have it as 1 plus 1 times half plus 1 times 2 to the power of 2 divided by 1 over 2 to the power of 2 plus 1 times 1 over 2 to the power of 3 plus this is just 1 plus half plus quarter plus 1/8 plus So as you probably remember a certain formula, the sum of geometric series is derived from this kind of method. So you have S equals this, right? So C times S equals AC plus AC squared plus AC to the power of 3. Remember that each time you have to time that by C. So plus this would be plus ac to the power of n, and then at the end it would be ac to the power of n plus ac to the power of n plus 1. So every single time this matches, and cs minus 1s equals c minus 1s equals the bottom minus the top, which is all of these would cancel out, and then you would be left with ac to the power of n plus 1 minus a, because this is the remaining, this is also the remaining, but this is remaining on s, this is remaining on cs. And then we want to move the c minus 1 to that side. So s, eventually we get the sum of this geometric series is ac n plus 1 minus a divided by c minus 1. To prove this theorem, you can also use induction. So let me rewrite the theorem that sum of a plus ac squared, ac to the power of 1 plus ac to the power of 2 plus ac to the power of 3 plus ac to the power of 4 all the way till ac to the power of n equals ac n minus 1, n plus 1 minus a, and then c minus 1. So to prove this by induction, remember we only need two conditions. One is that for n equals 1, the whole thing stays true. So all of the stuff on the top, so a plus ac to the power of 1, because of course n cannot exceed 1. And then on here it is a c to the power of, so right here it's 1 plus 1 equals 2 minus a, the whole thing divided by c minus 1. So that would equal, so this is the first, and then the second, that would equal a, right, we would take a out of this, a c squared minus 1 divided by c minus 1 equals a c plus 1 c minus 1 divided by c minus 1. So I can actually just remove the bracket here. So we get rid of the c minus 1, which is a plus ac to the power of 1. So this actually stands for n equals 1, because this one and this one are both a plus ac to the power of 1 when n equals 1. Secondly, we want to prove that if n is true, n plus 1 is also true. I want to prove that. So let's assume first, of course, that a plus ac to the power of 1 plus ac to the power of 2 plus the plus ac to the power of n equals ac to the power of n plus 1 minus a divided by c minus c minus 1. So let's assume that this is true, and then we want to prove that if this is true, right, then then n plus 1, substituting n, would also be true. So let's substitute that. So a plus ac1 plus the plus acn, and then we have acn plus 1 equals ac. So n plus 1 is what? Is just n plus 2, isn't it? N plus 2 minus a divided by c minus 1. So we want to prove that this exists given the condition that this is true. Not that this exists, sorry. This is true given the condition that this is true. So let's first cancel some things on the left and right. So as ac to the power of n plus 1 changed to ac to the power of n plus 2, essentially what this has done is just time that by c. So c times ac to the power of n plus 1. Essentially that's what happened, and then minus a divided by c minus 1. So if this is c times this, that means the original one, ac to the power of n plus 1 minus a, and then a plus c minus 1 to the power of ac to the n plus 1, not to the power, sorry, times ac to the power of n plus 1, right? That divided by c minus 1 should be the result, because this plus this together, right, is just c times ac to the power of n plus 1. So we can essentially just isolate that, this, and then this, c minus 1, ac to the power of n plus 1 minus a, plus, and then c minus 1, ac to the power of n plus 1. This cancels out. On the left-hand side, just a plus ac1 plus ac to the power of n plus ac to the power of n plus 1. And then, I shouldn't have written it there. I should have written it somewhere here. Okay. Equals. And then when you cancel out these two, it becomes ac to the power of n plus 1 minus a, c minus 1 plus, then you have already remained this ac to the power of n plus 1. So notice how in the very beginning, these are already equal to this because we assume that they're true. So assuming that this condition is true, we can just cancel all of these out. ac to the power of n plus 1, my goodness, equals ac to the power of n plus 1. Again, we proved that this is true. What we proved is that if n is true, then n plus 1 is true. If the condition that this is true equals this, then this equals this, which n plus 1 is true. So again, n, and then n plus 1, and then there's a new n plus 1, and you can prove that all integers bigger than this, right? This is like a starting point, and then you go, and then n plus 1 is essentially this starting point right here. So all the integers bigger than n equals 1, right? They are true for the formula of ac to the power of n plus 1 minus a divided by c minus 1 equals the sum of this geometric series. Let's look at a slightly more difficult so geometric series, it's okay. It's not really, like, it can be proved by induction. I think it's a pretty good small exercise to do. But I think something like the something like the sum of squares would be a pretty classic example to look at. So we already went over the sum of integers, so sum of integers, or let's say natural numbers because don't want to confuse ourselves. So 1 plus 2 plus 3 plus 4 plus all the way to n, right? This equals n plus 1 divided by 2. Sum of natural numbers squared, right? That would be 1 to the power of 2 plus 2 to the power of 2 plus 3 to the power of 2 plus all the way to n to the power of 2. I encourage you to try to figure out this problem on your own before coming to see the formula. But of course, formulas here. Personally, I don't hate formulas, but like I'm against just memorizing them. Well, of course, everybody is against that. Just because purely memorizing it doesn't really open doors for you to explore some of the other stuff, especially related to this kind of stuff, right? Because using this formula is essentially all that you get memorizing. You don't get to understand any part of it, you just memorize, that would not be the best outcome. So yes, back to the topic. So this will equal to n times n plus 1 times 2n plus 1 divided by 6. So Two ways we can prove it. One is by induction. The second one is by using this called binomial expansion. But firstly, I'll cover induction, and then as an extension, we will talk about the binomial theorem and binomial expansion and how that relates to this. Recall as before we used induction. We proved that n equals 1, this is true, that would satisfy, and then if n is true, then n plus 1 is true, and then that would satisfy. So these two together would mean that fn, or this whole thing, is true. First step, n equals 1. So this becomes 1 squared equals, this becomes 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. So equals 1, 2, and then this is 4. What is it, 4? Oh, 3. My goodness, I'm sorry. 1 times 2 times 3 divided by 6 equals 1. 1 equals 1. So n equals 1, true. Second step. N is true, then n plus 1 is true, assuming that this condition is true. Okay, assuming that 1 squared plus 2 squared plus 3 squared plus n squared equals n plus 1, 2n plus, was it 1? Divided by 6, assuming that this is true. Now we plug in n plus 1 as n. So 1 squared plus 2 squared plus 3 squared plus n squared plus n plus 1 whole thing squared equals, now n plus 1, right, as the n, and then n plus, what is it, 1 plus 1, right, because this is original, and then that plus 1, and then times, what is this, 2 n plus 1 plus 1, and then that divided by 6. This looks very tough. This looks very, very tough to solve. But it's actually just all right, because eventually we want to cancel out all of these, right? We want to cancel all of these out from here, because we're assuming that all of these, right, all of these equals this. So we just want to split the whole thing of this into this plus something else. Let's get started. So this would equal n plus 1 times n plus 2 times 2n plus, that would be 3. Is it 3? Yes. Divided by 6. So right off the bat, you can notice n plus 1 is pretty much the same as before. Remember, we want to convert that into this plus something else. So n plus 1, right? N plus 1, we want to remain that. n plus 2, we want to get the 2 away, because eventually we want this n to isolate and be free. So 2, we take that out. That would be n plus 1 n 2n plus 3 plus 2n plus 1 2n plus 3 divided by 6. And then now we want 2n plus 3, that minus 2 out there, because we want 2n plus 1 eventually. So n plus 1 n 2n plus 1 plus 2n plus 1 2n plus 3, this right here, and then plus, right, 2n plus 1 n divided by 6 equals, right here, this would be the original. So n plus 1, 2n plus 1 divided by 6. That would be the original. And then we have this, and then this. So, looks a little bit messy. It's okay. Plus 2n plus 1, 2n plus 3 divided by 6. And then plus 2n plus 1 n. So we will just rewrite everything here down here, plus n squared plus n plus 1 squared, and then this part right, equals to this part. So it cancels out, cancels out. So eventually we're at n plus 1 squared equals this. 2n plus 1, 2n plus 3, plus 2n plus 1n. So immediately we notice that this and this, we can basically combine the 2n plus 3 and n right here. So we'll do that right now. So that would equal to 3n plus 3. I did that very quickly, but feel free to slow down and verify whether if it's actually correct. I'm very confident that it's correct. So 2n plus 1 plus 3n plus 3. So, sorry, times. So 3n plus 3 could be split into 3 times n plus 1. So times 3 times n plus 1 divided by 6. And 6, 2, 3 could just be eliminated. So n plus 1 squared equals n plus 1, n plus 1, n plus 1 squared. Now we proved yet another sum. So just reviewing what we did here, we first proved that for n plus 1, this whole thing is true. And then we proved that if we assume that the n plus 1, if we assume that for any n is true, the number directly after it should also be true. The n plus 1 should also be true, right? N equals 1, that is true. And then for any n, right, the number directly plus 1 should also be true. So this could also be n plus 1, this also be true. So if this is true, this is true, and this is also true, this is also true, this is also true, this is also true, keeps going.